Hello, my name is Mary Ogborn. This fall, I will be a senior physics major at James Madison University, and this summer I got to work with Dr. Peter Diener at Louisiana State University on looking at extreme mass ratio inspirals. So extreme mass ratio inspirals are essentially the movement of a small compact source, in this case a stellar mass black hole, around a much larger source, in this case a supermassive black hole. These stellar mass black holes can range from about 3 times the mass of our sun to, let's say, 30 times the mass of our sun, whereas these supermassive black holes can be millions of times larger than our sun. So even this image that sort of is an artistic rendition of the space-times isn't even quite to scale. We would expect the stellar mass to be much, much smaller in comparison to the supermassive black hole. Now, what will essentially happen is that the stellar mass black hole will eventually go in some revolutions around the supermassive black hole and then inspiral and eventually merge with this supermassive black hole. And as predicted by general relativity and as directly observed in 2015, we know mergers of black holes will produce gravitational waves. So if we look at the current facilities that are able to measure these gravitational waves, we have LIGO. There are 2 facilities, one in Washington State and one in Louisiana. And LIGO does a great job, but it is limited by the frequencies it can observe. So LIGO is currently capped at observing mergers that have a total mass of about 100 times the mass of our sun. So this does not include the extreme mass ratios that would include totals of millions of times larger than our sun. So with LIGO, it can observe between 10 to 1,000 hertz, but with mergers for these extreme mass ratios, we're talking about millihertz. So there is a proposed space mission, the Laser Interferometer Space Antenna, which will be LIGO but in space, that could potentially have the ability to measure these extreme mass ratio mergers. Now, this will probably be launched around 2034, but it's very important that we start simulating data that can come from this, so that way we know what to look for once it starts observing. But when it comes to simulating these extreme mass ratios, there are a lot of numerical complications that numerical relativity cannot handle on its own. So we first have to deal with the short scale of space-time distortion by the stellar mass black hole. This requires a lot of higher resolution, which puts it at odds with the large length scale of the supermassive black hole. And then we have to deal with long time evolutions. So the evolutions, or the number of cycles it will take before a merger, is directly related to the mass ratio. So again, if we're talking about a stellar-sized mass black hole and a supermassive black hole, then we're talking about potentially millions of revolutions before we finally have a merger. In terms of numerical computation, numerical relativity takes too long to do this, so we have to turn to approximation theories in order to get an idea of how this will work. So Dr. Diener has developed a code. It's the self-force in 1 dimension. And this is one of the approximation codes towards simulating these MREs, or extreme mass ratio inspirals. So it does use perturbative theory, where we are starting to treat the stellar-sized black hole as a point source moving in the scalar field of the supermassive black hole. And using spherical harmonics, partial differential equations can be broken down from the original 3+1 to 1+1 dimensional evolution. However, all the harmonic modes that we're using still carry information, so at the end of the simulation, we can still reconstruct the 3D data. So we're not losing any information. This is simply for simplifying the amount of numerical computation we need to do. Now, this is also allowing us to do a self-consistent evolution. We can evolve the field and orbit of the particle, in this case, the stellar mass black hole, at the same time. This code is written in modern object-oriented Fortran. There are a couple scripts also written in Python. And on the right, you can see this is one of the many modules, or one of the many files that make up this code. This in particular is one of the grid functions. It's what I focused on for most of the summer, and I'll explain it in detail later. So my role in this project has been creating a checkpoint restart facility. Now, like I said earlier, these simulations have long time evolutions, and even on computers that have access to about 48 cores and with the simplest parameters, it still can take anywhere from 2 to 3 weeks for one simulation to run. So if for some reason this simulation stops in the middle, we want to be able to go to the last point it saved and restart from where it stopped rather than have to go all the way back from the beginning. In order to do this, I'm using HDF5. This is the hierarchical data format version 5. This was preferred over other things such as saving in ASCII because it is portable and binary, so there isn't really a limit on the amount of data that we can save. And it can run on single systems and also parallel processing systems as well. It's also interesting to know that HDF5 works with both C and Fortran, but also has its own documentation. So when I was writing this checkpoint, it was a combination of Fortran and HDF5 commands. Now the goal was to save certain parameters, which include the size of the black hole, what types of equations we're solving, as well as the grid functions, which play an important role. And then we also want to implement this checkpoint into the existing code. So these grid functions are very important in this code because they're essentially spatial slices that we can integrate forward in time. Now, the main purpose of the code is to solve the wave equation, which is technically valid everywhere in space, but numerically it's very impossible to solve everywhere from negative infinity to positive infinity. We want to discretize our space and set up grids so that way we're able to actually run these numerical simulations. So with these grid functions, we can set up our array of nodes that save actual data and define multiple variables in the same places. So there's a lot that goes into these grid functions. We have our value of n, which is our number of elements. We have our IOID, which in this case is a file output ID, so it allows us to track this grid function. We have the vname, that's just the name. And then we have a 1D array of, it's called elems, and it's a length of our number of elements. And within this elems, we have information about the order of the node, and then the var, which is another 1D array that's length of order plus 1 that also contains information from these spherical harmonic nodes. Now, in terms of saving this, it can be very difficult because our var is a compound data type, all the information in our elems is a compound data type, and then the actual grid function itself is a compound data type. So we have a compound data type inside a compound data type, which made it very hard for mapping between the actual data and HDF5 saving data. So here's the current status here at the end of the summer. We have been able to save a grid function, and we've been able to save these single parameters. If you look on the left, this is an example of what HDF5 likes to save. So at the top, we have our file, which is called checkpoint.1. Our data set's the grid function, and here we start looking at compound data types, which are our number of elements, an integer. IOID is another integer. Then we have vname, which is a string. And then we start getting into our elems, which is the other compound data type, which again is a combination of integers and real data. So as you can see towards the bottom, this is n, IOID, our string, which still needs to be edited so that way it displays an actual name. And then here at the bottom with the start of twos, we have our elems. So for future work, we need to determine what the checkpoint file actually needs. There are certain grid functions that we can sort of ignore. They could be reconstructed from our information already existing in the checkpoint file. We also need to read this checkpoint back into the code and make sure it works. So this essentially means, can it take in a checkpoint and start running the simulation smoothly? Or are there errors? Or is it missing a certain component that's necessary? We also want to expand this code to include Kerr spacetime. Currently, the code only supports black holes that are Schwarzschild black holes, which essentially means that we only have information about the black hole mass. There is no spin or charge. Whereas Kerr spacetime black holes include mass and a spin. And this is actually undertaken by another student in the LSU Physics REU, Show Gibbs. So this is future work that can be continued in these next couple weeks. Hopefully we can finally get one hold checkpoint file created and implemented back into the existing code. I want to say thank you to Dr. Diener for all of his help in this project. I would not have been able to do as much as I did without him. I also want to thank LSU Center for Computation and Theory for allowing this RU to happen. It's been very interesting, especially considering the current state. I want to thank all the other RU students for being a great social group. It's been really fun. And also want to thank the National Science Foundation for allowing this RU to even exist in the first place.
Okay, questions, comments?
What was it like using object-oriented Fortran? Have you used it before?
I've run some Fortran codes before, but I've never written them. So it was definitely, I was very similar to James in that I came from a Python background. So I was used to, seeing lines executed right then and there. I wasn't used to Fortran. So it was interesting. I'm glad I did it. Like, I think it's a really good skill I have now. But at the beginning, it was a little difficult.
Yeah, it sure does seem hard. That's pretty impressive.
More questions, comments? How large will be the typical data file that you would like to store?
I'm not sure yet, just because, like I said, certain grid functions can be saved, certain ones we can ignore. So I have to look into that more.
Any other question, comments? Okay, there are no more questions. Sounds Mary.